Welcome to Cheap Controls. We make videos on things that we struggled with, hoping to help you so you don't. Consider subscribing and hitting that bell. In this video I'm going to go over pulse width modulation. I have a previous video I did on just the Arduino using pulse width modulation, so I'm kind of considering this the second video in this series because I'm going to add it to the playlist, but it's been a long time since I did that one. And in this video I'm going to go over the PCA9685. I'm going to show how to do pulse width modulation with that, and I'm going to do it without using any libraries other than the I2C library that's built into the Arduino itself or into the IDE itself. And I'm going to break this up into, I'm not exactly sure how many videos. I'm envisioning it'll be a total of 4, including that old one. My next video is going to be over using the Nexion to control the pulse width modulation in the PCA9685, and then I'm going to finish up with a video going straight out of the Nexion and using the pulse width modulation that's built into it. The Nexion enhanced versions have some pins on it that can be used as pulse width modulated outputs. Well, hey there, Flutterbirds, get out of there. They're always bugging me. This will be my first time using a whiteboard, so we'll see how it goes. Put some comments in whether you like it or not. But in pulse width modulation, you have to think of it as taking a section of time, and we'll say, let's say this is like a microsecond here in time. And if your light is on, we'll say this is 5 volts. And this is 0 volts. So if your light was on, it would be on the whole time. And if your light was off, it would be down here and be on 0 the whole time. But with pulse width modulation, they take like 1 microsecond of time and they break it up into sections. And we're just going to split it in half for right now. And your light could either be on all the time or off all the time, or it could be on for half the time and off for half the time. And so if you think of a light, it would be dim now. It wouldn't be off, it wouldn't be on. But this turning of the light on and off would happen so fast that you wouldn't be able to see it with your eye. It would appear as if the light were just dimmer. And then let's just say we broke it up this microsecond into 4 sections. And then we turned it off here. Then it would even get dimmer. Or let's say we left it on until we got here. It wouldn't be fully on. It'd be a little bit brighter. This is the idea with pulse width modulation. Now with the chip that we're going to be using, they have an on time and an off time. And let's just go ahead and break this up into 8 sections instead of 4. And we're going to have 0, 1, 2, 3, 4, 5, 6, 7, and 8. And you could set your on or off time to be anything in here. And we're going to set our on time to 5 and our off time to 2. So when you would start your circuit, it would be off. When it hits 5, it would go on. And then you have to think that this section here is just going to be repeated over and over and over. So when it comes back in and it hits 2, it's going to go off. And then when it hits 5, it's going to go back on. And so your on time and your off time can be any number in here. It doesn't matter the order. But with the way it's set up right now, it's on for the 0 to 1, the 1, and for these 3 over here, and it's off for only 3. So in this case, it's on more than it's off. If we switch these around, and we turn it on at 2 and off at 5, it'll come in off, it'll go on, go over to 5, it'll go down, and now it's on for 3 and off for 5. So depending on the order that you do this, it does matter. And for my examples, when we move to the Arduino, I'm going to set the on to always be 0 or 1. So it's always going to turn on, it's always going to be on, or it's going to turn on right here. and then it'll go like this, and we'll select where we turn it off. So if we let it go all the way, then it'll be on most of the time. But if we turn it off at, let's say, 2, then it's going to appear to be kind of off or very dim, or we could just turn it off at 1. I've never set it to the exact same time yet, so we can play with that. But with the chip we're going to be using, that 9685, instead of 8 down here, there's 4096. So you take that short period of time and you break it into 4096 different steps. So even if it was off for that first one and then on for another 4095, it would appear to be on all the time. So we can fudge this a little bit if we're worried about an error. Sometimes I'll even make it 5. So it's off for that first 5, and then it's on for however long, and then it turns off. With this 4096, that 5, you could do 20 and you're not going to notice it. So this is just a brief introduction to pulse width modulation, and also a brief introduction for me on using a whiteboard. So we'll see how this goes. We'll see if I even put it in the video. Now we're going to switch over to the Arduino. First thing I'm going to do is go over just to show you how I collect the address of the PCA9685. I have a video already out on this, so I'm going to make this fairly brief. But what I do is I run this I2C scanner. The addresses in the I2C are from 1 to 128, so I just count those up. And then I just do a begin transmission to the address. And if I get a reply code of 0, then I know that it is a legitimate device that's out there. So you want to do this with only one I2C device out there, but it just helps you figure out and confirm. There have been times where I've spent a long time trying to figure out what's wrong just to find out I didn't have the address correct. And what we see is we see a device, the ID is 64. So we're going to use that going forward in the Arduino to run the PCA device. And that equates to 40 for hex. And now I'm going to talk a little bit more about the device itself and the way the memory is allocated on it. The way I think of the addresses on the I2C devices is I think of them as memory locations, because you're writing data to them and you're reading them. And they usually have a range of locations where you write that data to, and they stay static, and you get those in either the data sheet or you can hunt them down in different ways. If you use the libraries, it does make this a little bit easier, but I like going through this way because I learn a little bit more about the device itself. And for this particular device, the first 2 locations, 0 and 1, are where they configure the device and determine how it operates overall. And then there are 4 memory locations that we're not going to get into today. They're not really applicable for what we're doing here. But then memory location 6, which is actually 7 because it's 0 based, is where the first channel begins. And each channel is broken up into 4 bytes of data. And since the data range, the on and the off times, are 0 to 4096, that equates to 12 bits of data. And since the data is stored in bytes, it can only have 8 bits per memory spot. The first location for each channel is the lower order 8 bits of the on time, and then the second one is the last 9 through 12, or the higher order 4 bits of the on time, and then 8 and 9 would be the off time. It would be the lower order 8 bits and then the higher order 4 bits. And so the next channel would start at 10. And that's how it works. So you start with your first 2 bytes are the overall configuration, and then you start getting into the channels themselves. We'll go over the different bytes up here next. The one that we're really concerned with is the first location, is the 5th bit. And that's the only one that we're going to have to change because it's defaulted to 0. And the way I2C goes, when you write to a memory location, it generally assumes that you're going to write to more than 1. So the little counter in the I2C device will automatically increment to the next memory location. So you can just do write, 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 and you'll write to the 4 bytes. If you leave this disabled, you have to begin the transmission, you put the memory location, you write to it, and then you end the transmission. And then you have to begin the transmission again, put the next memory location, write to it, end the transmission. And you don't have to do that, especially in this case, because we know every time we write to it, we're going to write to 4 bytes. So we change this to enable auto increment. And then the other thing we change is this sleep. I just put it in normal mode. I don't want to deal with low power. I was messing with this, and it seemed that when I set that to 1, it shut everything down, which is kind of strange because when I first got it and I was messing with it, it seemed to work just fine in the default mode, except for I had to change the addresses each time. So this is something I want to look at later on my own. But for this video, it doesn't matter. But I do leave it to normal. And then everything else I just leave set to default. So I don't want to restart the device, so I leave that disabled. I want to use the internal clock, so I leave that at 0. And then these sub-addresses are just something I also don't want to really get into in this video, but I believe it has something to do with having more outputs. And then in this one, we'll leave this one enabled because this allows you to write to a memory location that when you write to it, it sets every channel the exact same. And that can come in handy sometime if you are using all the channels and you want to do a reset or something like that. Now the second bit, we're not even going to get into. We leave it set the way it is. The first 3 bytes are reserved. They don't really do anything. That's for future usage. The logic state, we want to leave that to be normal. We don't want it inverted. That would mean like whenever you think it's on, it's off, and I don't want to get into that. The output change, we're going to leave that on stop instead of acknowledge. And the outputs themselves are set to either, you can choose open drain or totem pole. We're not going to get into that with this video because it works fine with both an LED and a servo motor, and that's kind of the main reason people use this, so I just leave that alone too. And then these bits 0 and 1, that just kind of can change some things there too, but we're just going to leave that set to 0, 0. So in this case, we are going to write a hex 04 to that mode 2, even though it's defaulted, and I'll get into that when we get into the actual code in the Arduino. And then, as I said before, 6, 7, 8, and 9 are channel 0, and then 10, 11, 12, and 13 would be channel 1, or channel 2, because it's the second channel. It's, once again, these are 0 base 2, so it can get confusing. And then 14, 15, 16, and 17 are the next channel, and so on and so on. And then, as I said earlier, you can write to these locations, 250, 251 through 253, and that will set every channel to the exact same number. So if you were to write, you have to be careful with this, because if you just wrote to the lower order bit, which I spelled wrong here, but if you just wrote to that one, it would set all of them just to that one, and the other 3 would stay whatever they are. So if you're going to a reset state where you want the lights to always be on, then you'd want to write to all 4 of these. And when you write to all 4 of these, you're actually writing to every channel that you have out there. And now we'll move over to the Arduino itself. This isn't my normal setup. Usually when I'm doing something with the Nexion, I have a very strict beginning template that I use. But in this case, since we're not using the Nexion, although I will be in the next video, for this one I just have it pretty simple. And since we're not using any libraries, there's not a lot to this code, so it should go pretty quick. I do have my cheap control stuff over here, and that's where I have the BCD to decimal, decimal to BCD, and I can print binary. So I can take an integer value and print it out in binary. It's kind of a nice troubleshooting thing. But for this one, I added a word, so I can print out 16 bits instead of just 8. And that'll help us when we want to see the 12-bit values for the off time and the on time. I only have 3 variables in here, and one is the error, and I won't be using that in this video, I don't believe, unless something goes wrong. But I collect, when I end the transmission to the I2C, I collect that error in case there is an issue. I can use it for troubleshooting. We're going to count from 0 to 100, and that's how we're going to set our off time. We're going to leave our on time set to 0 or 1. I can't really remember where I have that set at. And then we're going to adjust our off time. And we're going to start in the middle of our 4095 range. And I'm going to use map function for that, but I'm going to start at 50. That way I can count from 1 to 100 and it'll make more sense, I think. And then our count rate's going to be 2. I can adjust this too if we determine we need it for the speed of the video, but I'm going to count in increments of 2. So it's going to go 50, 52, 54, 56, 58, and it's going to count up to 100, and then when it hits 100 it'll start counting with -2, so it'll start to subtract. In our setup, we use our wire begin to start our I2C, and then we start our serial monitor because I want to be able to show some data. That's how I'll show those bit values. And then in this area we set up the I2C, that PCA device itself. And the ID of the device is 64, but in hex it's 40. And so the first thing we're going to do is we're going to write the memory location we're going to write to, set the location to 0, and we're going to write that 20. So we want to change that bit so that it auto increments. But since it doesn't auto increment yet, I have to end the transmission before I can write to that second memory location, which we're just going to reset to the defaults. And remember, I said that I was going to do this even though I didn't need to. I just wanted to show you that setting it didn't make it happen. So we had to end the transmission, and then when we begin transmission again, now it is set to auto increment the memory locations. So when we get down below, when we write the on and off times, it will auto increment. And that's really all we need to do to get the PCA device or the pulse width modulator board all set up and running. I don't normally use a delay. I like to use asynchronous delays, but just for the ease of this video, I'm setting a delay every half second. So every half second we're going to change the pulse width modulated values in the device. And we're not going to count from 0 to 100. We're going to count from 5 to 95. So we're going to start at 50 and we're going to count up to 95. And once we hit 95, we're going to take our count rate and we're going to multiply it by -1, which will take that 2, make it a -2, and then we'll start subtracting. And then when we get less than 5, we're going to multiply it by -1 again, and it'll start counting back up. And then we're going to set our off time based upon this map function. And that just takes that counter variable, which is going to be a range from 0 to 100, and changes it from a range from 15 to 4,000. Now the value could be 0 to 4,095, but in this case you're not going to see much change in that last 95 or that first 15 values, so we're just going to leave it 15 to 4,000. And we're going to set our on time to 1, and the on time is going to be static. At one point I originally thought of maybe doing some math and doing some calculations on it, but we'll be getting into that with the next in the next video, so I just commented out that line, and I'm just going to do it with this map function instead. And then we're going to print out the off time, whatever it's set at, because that's the time that's going to be changing. So if we have an error, it's going to be there, so I want to be able to refer to it. And this is where we get into the meat of it, where we're going to write the data to that PCA device. So the first thing we do is we have to begin the transmission and identify the device. And then we have to set the memory location we're writing to, which is 6, because that's channel 0. And then the first thing we're going to write to it is the lower 8 bits of the on time. And we can do that by just casting it. So the on time is an integer which is 2 bytes long. So we're just going to cast it to 1 byte. We're going to write it into that location. And then the next time we write to it, we're going to be writing to location 7. And what we're going to do is we're going to shift that bits over 8 bits to the right. In other words, we're going to drop off the lower 8 bits. And then we're going to write that to the next location, so we'll just have those remaining 4 bits. And then when I do the off time, you'll see I have a little thing set up so I'll show you how that works. And then on the next write, we're going to write the lower 8 bits of the off time. And I think I'm going to move this up just to make it a little more clear. So just like up here where we shifted the 8 bits to the right and dropped them off and wrote the next 4 of the 12, we do the same thing down here. And then what I did was I added some lines down here to show you that in the serial monitor. So we're going to print line the off time, just the word off time. And then we're going to print binary in Word. We're going to print the off time. So it's going to show all 12 bits. And then we're going to print line just to lower it to the next line in code. And then we're going to serial print 8 spaces. And then we'll print the off time in bits, but only a byte of it. So it'll show what got sent when we did this byte off time, just like up here when we wrote the byte off time. And then we're going to insert another line, and then we're going to shift it over 8 bytes and print that out. So hopefully this will give you an idea of what's happening up here in order to get the first lower 8 bits and then the higher 4 bits. I'm going to turn off the auto scroll so it doesn't go crazy here. And you can see that what we have is we're sending the off time of 2087, and then it counts up to 2166, which is about what we would expect because we started it at 2000 or halfway through and we're counting up. And then when we write the byte, we're just writing these first 8 bits here. And then when we write it after we've shifted it 8 bits to the right, we're just writing this value then to the next memory location, which is this value up here. So it ignores these zeros, or it sends the zeros, but the value is really just this 8 here. And now I'll turn off the auto scroll, turn it back on, and you can see that it holds. So we're sending 3, and then this value lines up. So that's how that works. So we send the lower 8, and then we send the upper 4 bits of data. And you can see here that we just hit it at its lowest point. It doesn't come through very well on the video, but it went. Now it's on all the time. It's not actually on at its brightest now, even though it looks like it. I'm going to pause the video here until it comes back around again. And there you can see it's getting dimmer, and now it's getting brighter. Just to make it a little more illustrative, I'm going to move it up to the oscilloscope. So you can see that it turns on here and goes to 5 volts, and you can see that this is getting longer as the off time is decreasing. It's not the greatest oscilloscope, so you got to bear with me on that. But now you can see that the off time is increasing. And as this is happening, of course, the light is getting a little bit dimmer. Now if you notice that at, let's say, halfway, that the light is bright as can be and you can't really tell the difference, you can always adjust your counter so it doesn't count all the way up to 4095. And we'll get into that in the next video. But for this video, you can see that everything is happening the way we assume that it should be happening. We have the on time set to 0, so it always goes on at the same time. And then we're altering the off time. I'm going to go back to the code and explain it one more time now that you've kind of seen it going, and hopefully that'll help. If you don't want to see it again, go ahead and stop the video because it's going to be a review from here. And up here, all we're doing is we're setting those first 2 bytes so that we set it so that our memory automatically increments. And then we have our rate here. And as I said, you could adjust it here. Like we could change this to 50 so it only goes from 5 to 50. And then, because if you were noticing that, let's say that the light only changes on the first 50% of our duty cycle, then you could change that to 50. And for servos, you really have to look at that because servos don't use the full range. And like I said, in the next video, we will get into that. But down here, we're just writing to the 4 bytes. So we take that on time and we send it the first byte, and then we send it the upper 4 bits, and then we write to the off time for the next 2. And if we had another channel, we could just keep writing. If we were writing all 12 channels or all 16 channels, we could just keep writing them. And if we had them all dedicated or knew what they all were, we could just write them over and over and over, and it would just keep incrementing. So you could say, like, instead of having on time, you could have on time 0, 0, and then on time 0, 1, and on time 0, 2 for each of the channels that you're writing to. And then down here, I just did a little test just for fun, just so you could see it. We print the word, the off time, and then I put some spaces in there to show you how it lines up. How it lines up over here. And so that way you can see that we're writing the first 8, the lower end 8, and then the higher end 8. And it works pretty well. There's no library or anything to this. And I had a lot of fun making this one. I was actually working with a viewer's question to do this. And so the main question was how to control 2 different things from sliders on the Nexion, and like I said, that'll be the next video, and I want to get that out very soon. I'm going to try and actually get it ready and record it tomorrow. And then the final video will be running the Nexion directly pulse width modulated out, and to be honest with you, I've never done it, so I'm not 100% sure what kind of load it can run. So the Nexion video tomorrow, where I'm running it through the Arduino and using this PCA board, I'm going to use a servo and get everything set up as best I can, so that way when we use the Nexion itself, I can see if it can handle running a servo or not. Well, that's about it for this video. If you like what you saw, consider giving me a thumbs up, and also consider subscribing to the channel. Thanks for watching.